with Michelle.
Then we have a design which we tape out that includes a on-chip TVS. Resistor consists of a resistor and a diode, and it needs to dissipate a large amount of power, and we weren't sure how would it survive. And so we were thinking using InVar to perform analysis and perhaps improve the structure. And we were working with Michelle. The first order of a demo, which is a simple scan D flip-flop cells. So we have knowledge, but we have some questions. Many, and then he left. So let's say you are the application support, but we like to learn of the InVar at this demo. So we can go ahead and create our own, simulation bench and perform the analysis. I'm sure along the, this process, we have many technical questions, which, we might come back to you.
Okay, so let me continue from here. So I'm actually managing the whole InVar development team. A few days ago, Peter just asked me what is the status of this, because we were helping Michelle to go through this. I got some time ago, again, some data from Michelle. I don't know how complete is it and what is there, but I ran analysis with this data. I ran it in several modes. So if Michelle told you we have several modes to run, one is prime mode, that is essentially spiceless. It's just layout resistivity analysis. And the second mode is mode when we run design with the spice simulation. So we get actual current consumption data from spice engine that is employed in InVar. These two types of the analysis, and I am ready to share with you one and another. If you have any questions, and your questions might be different from what I show you, so please just ask your questions. So my goal is to make your understanding and your understanding of the tool more clear, so whether it fits or not what you need. Okay?
Okay, that sounds share your screen. We don't see anything. Share screen in the middle.
Absolutely.
Give him presenter privileges.
And I mentioned that we're going to record the meeting for our own training purposes, if that's okay with him.
No, that's absolutely okay. There is no other customer data on the screen except yours.
Okay.
Okay.
So,
yes.
This is what I got from Michelle. You can see the screen, right?
Yes.
This is what I got from him. This is GS. So, for GS we had to create layer map. We have to create layer map for GDS because GDS has no knowledge of layers, layer order, how layers are connected, what are the types of the layers. These are just layer numbers. For this, I helped Michelle to create layer map based on his input. So we have in this layer map list of meta layers and connect via layers. Assign them names in the first column. We assign a layer purpose on the second column, and then we say that these names are actually for this GDS layer and this GDS data type.
The coming from the process menu of the TO6 process, right? And
I do not know. That's what typically customer does. So customers figures out what are the metal and cut layers in the design. And then actually customer builds this layer map. So naming layers from GDS layer numbers and mapping them to open access mask numbers. What mapping happens, because in open access, these are real masks, these are not GDS layers. You may have single mask when you manufacture the chip. You can create single mask from multiple GDS layers. And we do support this feature, so we can map several GDS layers into single mask. That's why we have GDS mapped to mask numbers. But this is simple process actually. So you, as you are in design, you can understand it really quick. I understand that you did not create this layer map, and this was created by Michelle so far, right?
Mm-hmm.
Okay, but this is a really simple step. This is what I had to create for GDS. We are done. The next one is ITF. So what I see, it has like a technology name, X6, so it's probably XFAB, right?
Yeah.
So yeah, that's XFAB. And the original like XFAB ITF. So we read ITF from Foundry directly. So again, there's nothing special to be done. And in your case, you see conductor layer names and via names. They match what we have in layer map file. So that's a good practice. If they do not match, you would have to create layer mapping file, but that's not the case for you. A layer mapping file. So that's technology data. But let me get back to the technology data. You may have pretty complex ITF. This one is very simple, but from ITF, for the purpose of airdrop analysis, we use only few numbers. So thickness we use mostly for thermal analysis. For airdrop, we are interested in minimal feature size on the layer, and this is actually defined with the W mean and the S mean, because we do like our internal fragmentation of geometry based on this. And what is also important is RPSQ or RHO. A single value, it could be table, so we support both. In your case, it's simple RPSQ, so that's essential. Dielectrics, these are mostly fillers between layers, so we do not use it for airdrop. Here's activity information from what layer to what layer, and also resistance per via for given area. So this is what we also use for airdrop calculation. So that's pretty much it.
Okay.
Any questions?
No.
Okay, so let's move on. So we're good with ITF. We just covered what's in there. The next one is SpiceNet list. For SpiceNet list, we have seen in his original data. I don't know who did actually extraction of layout. Who did DSP? You or Michelle?
I believe Michelle extracted.
Okay. So I have what I have. So in your original SpiceNet list, what we have, and what we really need to have. We have extracted DSPF. You can see it on line 3. You may have some libraries and supplementary subcircuits included. And then we have to define supplies like GND, GNDA, GNDB, If in normal case you just say that this is global zero for us, for InVar, a power supply should be defined as voltage source between node 0 and specifically named node, GNDA, VDD2P, VDD2N, and so on. There is one limitation of the tool. In your original netlist, VDD2P and VDD2N were described as PWL, so you probably were trying to simulate a ramp-up process, power-on process.
Right.
Yes. For InVar, currently there is limitation. We work with a stable voltage. Calculate airdrop for constant voltage and operating circuit. So for this we had to replace, or Michelle actually had to replace this PWL ramp-up profiles with static voltages. And this one, I see it just probably remains intact. And for this in 0, in 1, the bottom, these are signals, so they were left intact. So signals, waveforms are okay. And we instantiate a circuit, that is essentially DSPF sub-circuit. And there are statements like temperature, transient simulation parameters, and that's it. We do not require anything else on top of this.
Okay.
So then, we have two modes of analysis. In mode, we use just GDS tool layout. Let me show you the script for this. Again, script is very simple. Analysis script. Show you results of both. What we do to set up analysis? You can see we read in GDS2, excuse me, in the line. We read in technology data. So read in ITF, so we know all the layer attributes like resistance, minimum feature size, and such. We instruct the tool that this is analog design because we support different types of the designs actually. And then for given design scope, here design scope for design, because we read in hierarchical GDS and there are many designs in this GDS and hierarchy. So we set scope on this design. And we instruct the tool to fit into the nets, all the nets that you use. And they assign these nets either power type or ground type, and for power we assign nominal voltage for this net. And we say that we will do just one analysis and one analysis view, and assign like arbitrary name AV to this analysis view. So it's pretty much it. At this moment, we read in the GS2 layout, but we do not read SpiceNet list. We read SpiceNet list because we would like to run very quick, accurate, the representative analysis of a supply network. How good is supply network? For this supply network, we set up airdrop environment. So every supply net, we define location of voltage sources with different ways to define voltage sources. We can use default paths, we can specify exact coordinates, layers, we can specify specific text, label text on specific layers. So it's quite flexible. For this one, I use just default paths, voltage source list with the nominal voltage and resistance. And for all the 6 nets in the design. And because we do not read any SpiceNet list, and tool doesn't know what's the current consumption of this circuit. We run analysis with the current consumption. So actually output of interactive functionality in GUI. I'll show it. I will it later. So we find areas on given metal layer for given net, and how much card would be consumed within this area. And this for all the nets, very simple. And then analysis. What do we have then in the result of this script? So find this one. Okay. That's with the spice. That's the spice. This one is prime. Okay, so we open UI.
I have one question on that current source location. How do you select those locations?
For locations, very easy. First of all, that either customer provides, because if you take a look at your GDS2, you have text labels. Right? You know exactly locations of the pads where voltage sources are connected.
Yes.
So you can either say that at this coordinate, at this layer, you would have voltage source, and you can define multiple voltage source for every net. Or can if you have unique labels on designated layers, you can say just default pads, and this would be okay also.
Okay.
Or you can say, so there are different ways. I can explain it afterwards, but we have very flexible assignment of voltage source locations.
Okay, got it.
Okay. Let me run this one. Oh, no. So run itself is pretty fast, and we will go through. So which temporary data do I use? Oh, I use TMP. Sorry, I have to change. TMP is very limited in size. Change it to in case we create our IT create very small piece, so that's left over from this one. So this should be good. So now we have plenty of temporary data. So this is also important. The header, when you start the tool, you have on the second line from the bottom this PVT configured variable, and it tells where it points to. So open access is file-based system, so it requires some disk space to create temporary data. This is what you have to pay attention to, that file system size is adequate and has enough free space to run the tool. In my previous case, I by mistake set it to TMP using some previous runs. And TMP has very little free space left, so that's why I had this problem. Go through the whole analysis actually in front of you. That's pretty quick, so run it from the very end to the very end, so you get understanding of what performance of the tool, what's the runtime of the tool on this data is. As it's on analysis stage, it's processing geometry data to create airdrop graph. So the airdrop graph extraction here in the log file. So we are pretty much ready to run analysis, and in less than 1 minute it's going to be done. Okay, we are done. It prints some reports that were included in the script. But let's open the layout. So that's your layout. And out you can see all the layers. We have just regular layout viewing capabilities. And you can see we have all these labels. So NDA label here. Yeah, right here. So that's location of one GNDA connection. NDA label here, 4 A out labels here, 4 B out labels there, and so on. So these are labels that will be used for creating voltage sources. And as you remember, no, not this one. Where is it? This one. Yeah. Here I have it open. Yeah. Yeah. So when we say default paths, it actually was looking for the condition labels, and it assigned voltage sources at these labels. Then next, beside assignment of voltage sources, we assign current consumption. There is interactive tool. Also this. This is how we actually do it. You open menu. For example, you need to define voltage sources for net VDD. The tool gives you like ability to interactively define it, and you can define multiple current source areas for VDD, or a different shape where you have current consumption value, you have metal layer, and so on. So I assigned this just over the whole chip. I have no knowledge of this chip, so I prepared just demo, and you know it better. So let me solve this. Close this. Make sure. Based on this assignment of current sources, and they are actually uniformly distributed. We do airdrop analysis. See how airdrop analysis looks like in this case. So we have, let me preserve only DD net to start with, and all metal layers. So this one is pretty much okay, but if you look at the range of voltage drop, you see that maximum voltage drop in this configuration, I may have created incorrect configuration. I accept it. For this one, we see huge drop of 0.7 volt. So let's see which net is it. You can look into the report, and the report down there, that this is actually GNDB. Net shows such excess drop for given current consumption configuration. So let's turn on this net. GNDB. Okay. And that's what we see. Examine the location of voltage sources for this net. Turn on layout. So there are two connection points for GNDB. We check, then there's very narrow segment connecting these voltage sources with a pretty big metal area. And for this area, because I created uniform distribution of current sources, tool assumes that the proportional share of current is consumed by this area. It might be wrong assumption, but when you are a designer, you can assign it better. It says actually what you see, that such a narrow connection to this area is not adequate, assuming this model of current consumption. So it helps you to estimate eventual airdrop problems even at the stage when you just create your power plan without using any SpiceNet list. So
I have a question on the area you assign to a current consumption. So
yep.
So when you cover the entire chip, and so the current, I'm assuming the current standard voltage source, and try to find back to the grid.
Yeah, exactly.
And so the current, I remember you assigned 100 amps. Is it?
Milliamps.
100 amps.
These are just placeholders. So I don't know what are the real numbers.
Oh, okay. So if I don't understand. In real case, I would definitely change the area.
Yes, obviously, and this is what I actually is going to do. So let's say my assumption was wrong, and you as a designer, you know better that this consumption of GNDB is mostly in this area.
Right. It was the green and yellow area. The no metal 9 is connect to our protection metal 1. It doesn't do anything. It's an open metal. So
should it be here?
Yes.
So it's here. So how much current would you expect to be consumed in this area?
Full load, I would expect around 50 milliamps.
50 milliamps. So see, we say that in this area we would expect 50 milliamps flowing down from top metal to metal 1. Okay?
Mm-hmm.
Okay. Just area, and you can, by the way, you can fine-tune this. You can zoom, and you can fine-tune, and you can create multiple areas. So it's not limited to single area for every current, for every voltage source. For our customers, they create like up to 50 different areas in different locations. So to make it really accurate. But nonetheless, so let's rerun analysis. And this is pretty quick, and this is a very good exploration tool actually. So run analysis again. It would take just minutes. Oh, we see this. No, not put focus. We see this distribution of airdrop, and if we go to airdrop tab, we pretty high airdrop in this area. This is most likely because of the fact that these segments are disconnected on top metal. So what we have, at I watt. We have very narrow connection from these vertical bars. Is on metal 2. And
yeah.
But my current distribution model is wrong.
Yeah, I think we do have the protection metal as well underneath.
But you see here it looks like separate, and only these segments connect vertical structures. Fully disconnected on the top.
Right, should be metal L, and I think in the metal 1. So can we look at L instead of
okay.
1?
So there is nothing on metal L. So layer nothing, metal 2 nothing, and only metal L is actually metal 1 actually is present. There is nothing on the top metals. So let's check layout. Metal L. So that's what we have, and this is GNDB. GNDB is fully disconnected, so this is disconnected segment. It has only vias go metal 2, L2 is also disconnected, and it has obviously vias to metal 1. And the whole GNDB from here continues on metal 2, metal 1 only. So nothing on the top, so it's metal 1, fully metal 1 connection.
You are right. Oh, okay. So Yun, can you point? We have ground B, 1, correct? And then the.
Yep.
Can you turn on your? Can you?
So what would you like me to do?
Yeah, hi. The ground has the 1, and the L is connected to the input. Is the register.
So what was the question?
So L is not connected with the ground.
Metal L has only connection pads, and all these connection pads. So let me show it again. Looking at layout now, just layout. So L for B, it's only one metal rectangle. This metal rectangle has vias. This rectangle to metal 2. 2 is also isolated island of metal. It's not connected to anywhere. We are just looking at layout. Isolated metal island. So let me make it outline. This isolated island is connected through these green vias to metal 1. And from metal 1, it now continues like everywhere. So we go to AdDrop, we can see only connectivity of. So this is how actually layout belonging to GNDB looks like on all metal layers. Actually, the geometry that spreads through the chip is only on metal 1. metal and metal 2 are only like connecting pads.
So would this look like ground ground B bus?
Yes, this is how your GNDB layout looks like.
Yes, because our metal L is connected to A out and P out, so we use
But anyway, what I see, the whole area, this red-green area, is connected with the voltage sources to this very narrow segment. So
yes,
that
the area is the dummy, the metal one, the short small round,
you say this green red area is dummy metal,
Yes.
and we should not assign any current sources in this area. You just instructed me to create current consumption in this area. So where actually GNDB has most current coming from? Which area?
Bottom.
The bottom? We were wrong then. So this is a dummy metal area, right?
Yes. In the middle is dummy.
Okay. Then where most of the current consumption comes from? From here?
Oh, the screen is gone. That part.
So let's make most of the consumption here on metal 1 and analysis again. So see how it would affect. Okay, so in this case we see pre-current voltage drop for this one, and if we check everything, so we see like much more distributed, but again it depends on you as a designer. So in this mode, without using SPICE, you define what areas consume what current.
This looks much closer to what we expect for 15. I forgot how much resistance we extract. I have it in the DSPF file, but we can. This essentially is the same. Should be the same resistance as the high-pass extract parasitic. About misleading your your analysis. That's why I have Yun here. She's very familiar with layout. I look at them, but it's been for a while, so yeah, I forgot.
Okay.
Yeah, so this looks real, I think.
And we do not have covered also run with the SPICEnet list. So fortunately, we have a very short time left. So if you would like to have also a session about running with the spice simulation, you probably have to schedule another 1 hour session for spice simulation run.
What do you think would be best?
If you are okay, we can do tomorrow early morning. So for me, it's 8:30 a.m. I'm okay with this tomorrow. If I'm tomorrow.
Yes, 8:30 a.m. or 8 a.m.
We have time difference. So for me, it's 8:30. So for you, it would be the same time as today.
8:30, I think. Okay, that's great.
So
Before
let's do it tomorrow, so we won't delay you from.
One last question is, this model seems to me is assuming the current is uniformly distributed. There's no current routing, right? If consider the thermal effect as well.
No, but let's cover it tomorrow.
Okay, sounds good.
Okay.
See you tomorrow then.
Okay, see you. Thank you.
Great. Thank you so much.
Bye-bye.
Thanks.
Bye.